Next, I want to move on a little bit to talk about jump straight into photoelectric effect, right? Because of the failure of classical wave theory, Einstein, building on the work of Max Planck, postulated that light is a particle, right? And in physics, we can't just postulate, right? We try to confirm it with an experiment, and so Einstein's photoelectric effect, the theory, the equation, and the experiment garnered him a Nobel Prize, uh, right? Later on in his life, right? So let's first talk about the photoelectric effect in general, and then let me talk about light and photons, right? So in this part, I will be breaking down the Einstein's photoelectric uh, equation into three main parts, right? The light and photon parts, the metal part, and the electrons part. Okay. Yeah. So one of the guiding questions is, how does his idea of light differ from light in a classical sense? Okay. So overview, conservation of energy, right? Is that this whole idea that Einstein have is actually very simple. It's actually the conservation of energy, right? If you were born maybe 100 years earlier, maybe you would have been the one, because this idea of conservation of energy, practically everyone knows it now, right? So what is the idea? The idea is that the energy of the photons coming in, right? Remember, it's a photoelectric effect, right? It is about light giving electrons, right? So the actor is the photons. The metal is what is acted upon, and the result is the emission of electrons, right? So conservation energy. So if you have 100 units of energy here, and you give 20 units to the metal, the electron should have 80 units of energy. Okay. But of course, this experiment is not as simple as that. There are a lot of nuance here. And in this first part, I'll talk about the energy of photons, and I'll talk about this key ideas, which is number one, the equation. Energy of photon is given by HF and Hc over lambda. And next, that I'll relate how power and intensity relate to the rate of arrival of the photons. Okay. Right, so first, Einstein explains photoelectric effect, right, by saying that, okay, light is not a wave anymore. Light is made up of photons, a particle, each of energy hf, and when they hit a metal, an electron comes up. Okay, and he's saying that, okay, the energy of the photon has energy hf. Some energy is paid to the metal, so the energy of the photoelectrons, right, is hf minus the energy paid to the metal. Okay, right, and hf, the h is a Planck's constant. This is given to you in your formula list and your data list, right? So you have this value, and it is fun fact, it is the smallest constant that we know of as of now. Okay, and actually another interesting fact is that this Planck constant, it really pops up in many equations, right? And which makes people question, like, oh wow, what is about this Planck's constant that makes it so important, right? And Planck, another fact is that it's named after Max Planck, a very, very important scientist who made who actually pushed forward quantum research quite a bit, right? Right, so let's talk about the nuts and bolts, right? Let's talk about the definition. The photon is an indivisible quantum or packet of electromagnetic energy which is emitted, transmitted, and absorbed as a whole. Okay, what this means is that if you have a photon, that photon either gives you all of its energy and destroys itself in the process, or does not give you any energy at all. It cannot give you, say, okay lah, I give you half my energy. It cannot do that. Okay, it is one whole thing. Right? It's all or nothing, indivisible, and it's a packet of electromagnetic energy. A lot of students like to say it's an indivisible quantum of energy. missing out the keyword of electromagnetic energy. So you have to write that in. Okay, and the equation is given by E equals hf. Very, very simple. Okay, all right. And F, H is Planck constant. I've already introduced that to you. F is the frequency of the electromagnetic radiation. Okay. So find the energy of a photon of orange light of wavelength 600 nanometers. E equals hf, right, does not get you the answer because you realize that you're given a wavelength. So how do you convert frequency to wavelength? Well, you use the equation V equals F lambda, right? And hence F is V over lambda. But in this case, the velocity of light is the speed of light, right, which is a constant again. So this is 3 times 10 to the power of 8. You can write that in immediately and you get your answer, right? So here I've expressed energy in joules. You can actually re-express energy in terms of other forms like EV, right, which I'm doing now, right? This is actually a reminder. I believe that in electric fields you have learned this, so this is not new, but by now you must master this concept that the unit of electron volt is the amount of energy or kinetic energy that electron gains when accelerated through a potential difference of 1 volt. And this conversion is very important, right? It's like you convert 1 Singapore dollar to how many USD, right? You must know this conversion rate so you'll not get conned. So same thing here. So 1 EV, 1 electron volt is 1.6 times 10 to the power minus 19 joules. So in example 1, right, I found the value to be this in joules. I could actually divide it by this conversion to get the 2.08 EV of energy, right? So I can say that the light, also the photon, has an energy of 2.08 EV. Okay, right. So this is a explanation of the definition, right? It's the amount of Ke gain by electron when accelerated through 1 volt of potential difference. So if you imagine, right, why this is true, is because of your understanding electric fields, right? The loss in electrical potential energy is the charge, right? Charge E times the potential difference V, EV. That's why they name it EV. And that loss becomes the Ke. Okay. All right. Next, let me talk about the relationship of energy of light and photons. So with the understanding that light is now made of photons, we can actually calculate the number of photons, right? Isn't that cool? Right? If I look at light and I say, oh, this light is of a certain amount of energy, I can actually calculate how many photons there are in space. And just for fun, why don't you make a guess? You look at the light bulb now and say, okay, how many photons are there? 100, 1,000, a million? Well, the close answer would be billions and billions of it, right? The number is huge because the amount of energy you have, right? Each photon, right? For whatever light bulb you have, let's say you have 1 joule of energy in light. The light bulb, each photon has like is so small in terms of energy. You saw that the energy is in the 10 to the power minus 19 range, so you have billions and billions of photons to make up that energy. Okay. So let's look at it. A light bulb emits light of mean wavelength 4.50 10 to the power of 7 meters. The lamp is rated as 150 watts, right? And 8% energy appears as emitted light. How many photons are emitted by the lamp per second? Right, so energy of 1 photon using hc over lambda, you get this value. Nothing new, just practice. So in 1 second, right, how much energy is produced by the lamp? If it's 150 watts and it's only 8% efficient, right? The classical light bulbs, right? They are not very efficient. The modern LED, they are closer to 100%. So we use this for the classical light bulb. So 0.08 is 8% times 150. So you have 12 joules worth of energy in 1 second. So how many number of photons are there? Right, large number, right? 12 divided by 4.42 times 10 to the power 19, you get such an incredible number. 10 to the power of 19 number of photons per second, right? That this number is so incomprehensible, because can you imagine a million people and then you multiply that by another million by another million? Yeah, that's the number of photons that you have, right? Right, so next let's talk about the intensity of light and photons, right? Because intensity is one of the commonly used terms in quantum physics. So intensity, as we define in waves, is power over area. Okay, so power is energy over time. So you can say that intensity is energy of all the photons divided by time and area. But the energy of all the photons is just the number of photons times the energy of a photon. So if you rearrange, you can get n over t, the rate of arrival of photons, multiplied by energy of a photon divided by the area. Okay, so intensity is the rate of arrival of photons, n over t, times h over f, times hf divided by area. Okay. Yep. Probably some typos over there, but not a big issue. Right, just a rearrangement of it. So lastly, for quantum questions, generally you assume that the area of light that is incident on is constant. Right, we just assume that. If not, this would be a troublesome thing to think about. In my years of teaching, I've not yet seen a question that used area yet. Not from A levels. Right, next. Since we already have this idea that intensity is n over t times hf over area, where n over t is the rate of arrival of photons, we can conclude, and this is a very important conclusion, that if you double the intensity while keeping f constant, you will be doubling the number of photons arriving. Okay. Number two, if you double the frequency of light while the intensity stays constant, the number of photons must have been halved. Okay, and this is something that a third point that I want to bring is that in Cambridge, when they say I double the intensity, even when they didn't say that the f is constant, and especially when they didn't say that f is constant, you have to make the assumption, or you have to realize that most of the time Cambridge is making the assumption that frequency is constant. That means they are only doubling the number of photons that are arriving. Okay. Right. So at this point, I've covered for you energy of photons, right? Hf, hg over lambda, and I've related how power intensity relates to the rate of arrival of photons. So with this, I think we've come to the end of lecture 1. Right. Thank you very much.